An engine can sound perfectly normal. No warning lights, no smoke, no misfire. Yet, deep inside, a failure may already be developing. Engine bearings are critical components. They carry extreme loads, operate at high speeds, relying on a microscopic oil film to survive. When they fail, the result is often catastrophic. In this video, we break down how engine bearings actually work, what physical forces act on them, why lubrication failure happens, and how a tiny breakdown can destroy an entire engine. Most crankshaft bearings in automotive engines are plain journal bearings. They do not roll, they slide. Between the crankshaft journal and bearing shell, there is no metal-to-metal contact under normal conditions. A hydrodynamic oil film separates surfaces. As the crankshaft rotates, oil is drawn into the narrowing gap. Pressure builds. A stable oil wedge forms. This oil film carries the entire combustion load. At high RPM, this system works remarkably well. Bearings handle forces equivalent to several tons during peak combustion. But this only works if oil pressure is stable, viscosity correct, temperature controlled, and supply uninterrupted. Remove one condition, the system destabilizes. Clearance between crankshaft and bearing is only a few micrometers. That microscopic gap is everything. If oil pressure drops or viscosity decreases, the oil film thins. The lubrication regime shifts from hydrodynamic to mixed, then to boundary lubrication. Once metal contact begins, friction rises dramatically. This causes localized heating, smearing, material transfer, and rapid wear. The bearing overlay, a sacrificial layer, begins to deteriorate. If process continues, the bearing can seize within seconds. This is what drivers call a spun bearing or total engine failure. Engine bearings are multi-layer components, steel backing for strength, intermediate layer for load, and soft overlay for protection. The soft top layer can absorb small debris particles. It can tolerate short-term boundary contact, but it is thin. Once worn through, the harder underlying layer is exposed. At that point, wear accelerates exponentially. The system no longer protects itself. Engine bearing failure is rarely random. Typical causes include low oil level, incorrect oil specification, oil starvation during hard cornering, high oil temperature, contamination with metal particles, and excessive engine tuning without lubrication upgrades. Performance engines are particularly vulnerable. Higher combustion pressure increases bearing load. Higher RPM increases shear stress. Higher temperature reduces viscosity. Margins disappear quickly. Once disassembled, damaged bearings show. Deep scoring, wiped or smeared surfaces, bluish discoloration from overheating, embedded debris, and severe journal damage. Often, by the time audible knocking occurs, the crankshaft is already damaged. Repair costs escalate rapidly. A single bearing shell costs very little. But failure means engine removal, crankshaft machining or replacement, complete bearing set, gaskets and seals, and extensive labor. Repair bills can range from several thousand to well over $10,000. In industrial systems, the same lubrication principle applies. Only the financial scale increases. Engine bearings do not fail instantly. They fail progressively. A microscopic oil film, invisible to the eye, determines whether an engine runs for hundreds of thousands of kilometers or destroys itself in seconds. Technical systems rarely collapse without warning. They degrade under load silently until the protective margin is gone.